All right, physics fans. Today we're learning about work causing a change in energy. Oh, here's that bright owl again. He's a reader. Look at that. So we're talking about work energy theorem, how work can change one type of energy into another kind of energy, and the power of that to find information about forces, displacements, or energies. So here we go, guys. Hey, here's a coach, the ninja. Six Flags over Georgia. Haven't been there. So we're going to look a little bit at potential and kinetic energy and the conservation of that in another time. But today it's about how do you find the potential energy and kinetic energy, because work causes a change in either of those or both of those. So here we go. All right, after completing this little thing, you're going to define what kinetic energy is, what potential energy is, and make sure you're using appropriate units for those, for the metric units and the non-American ones. And the relationship between this work and energy. Remember, work is how you keep track. It's the bookkeeping side of energy. That's all work is the bookkeeping side. It's keeping track of what energy has been transferred from one pile of energy into another pile of energy, because according to the law of conservation of energy, it's always there. We're just moving it from one place to another by means of work. Okay? It doesn't mean it's going to be conserved energy or usable energy, but the energy's there. All right, here we go. So energy's ability to do work cause some kind of a change. Okay? So we can exert some kind of a force over a distance. Alrighty, so there's a truck that can do some work. More stuff that can do work. You can do work. So energy is the capacity to do work. Alrighty, so potential means you're not doing squat. It means you can. Doesn't mean you have to use your potential, but it's there. So it's the ability to do work by virtue. Now, depends on what kind of potential it is, guys. I've got chemical potential energy stored in my body right now. But today, we're going to talk about the gravitational potential energy. So it's due to your height then, okay? And what planet you're on, because it depends on how strong the gravitational field is. Oh, look at that, spinning a weight and going to work at the same time, maybe. Oh, going to take care of his butt. Look at that. Bam. And I don't think that's Cupid. So there's gravitational or gravitational potential energy in the mass here. This is a different kind of potential energy. It's called elastic potential energy. That's still going to be another week and a half away before we start learning about how elastic things store energy, convert that into kinetic energy, that arrow, and do some work, maybe knocking that weight out of the dude's hand. I don't know. He's looking kind of threatening with that weight up there. Alrighty. So a quick example on gravitational potential. There's a tall building there. So what's the potential energy of this 50 kilogram person that's 400 meters above the street? So keep in mind, gravitational potential energy is relative. And you can pick your zero to be anywhere. You can pick your zero to be at that 480 and call that the zero. And then if you had jumped off of this, you'd be going in the hole below zero, or you'd go and hit the ground at a negative 480 meters below. Or you could say, okay, the zero's in the middle of the building, and then this person starts out at 240 meters above that, but ends up at negative 240 meters. The displacement's still 480. My point is, gravitational potential energy, it's relative. And you put your zero wherever it makes the problem the easiest. So we're just going to put the zero at the ground level of this building, so the person's 480 meters above that. So to find the potential energy, it's the same as the work you would need to move that person up there. So the work is the weight of the person, 50 times 9.8 or 490 newtons, times the height. So that's the output work done, or the gain in potential energy. So that person climbing up there would change the chemical potential energy in the body by doing work into a gravitational potential energy. Or it could have used the elevator to get up there. It means the elevator did that amount of work. And so how much work is that? Well, it's the 490 times 480, which is 235. You say, hey, that doesn't look right. That's not a very big number. Kilojoules, guys, kilojoules. That's 1,000. That's 235,000 joules. So make sure when you're doing this math stuff with your energy that you're in standard mass, not grams, not micrograms, kilograms actually is standard. Okay, meters, seconds, and so on. So make sure you're in your standard units there. So an elevator would have to do that much work at minimum to get the person up there. In reality, the elevator's not 100% efficient. It's going to do a lot more work than that. But this is the work done on the person, the output work, which is the gain in potential. Okay? So work causes a change in energy. So that work changed it into a gravitational potential energy by climbing those stairs or however that person got there. All right, kinetic energy. So the other formula made perfect sense. It's your weight times your height. That's work. This one looks trickier. Okay? So it's your energy you have because you could ram stuff and move stuff around and do work on other things. So it's your energy that you actually are, something is happening, you're moving compared to something else. Once again, guys, this energy stuff is all relative. Because if I'm just sitting here and say, hey, Olson doesn't have any kinetic energy because he's not moving. Well, I'm going 67,000 miles an hour around the sun right now. Right now in Kansas, because we're spinning on the axis of the Earth, I'm going about 850 miles per hour. So its kinetic energy is, once again, also relative. So we usually say relative to the surface of the Earth. Okay. So to find how much kinetic energy a bullet would have, just a puny little 5-gram bullet going 200 meters per second, which is like 400 and some miles per hour. Not super fast for a bullet, but still it's good speed. So to find the kinetic energy, it's a 1/2 the mass times the velocity squared. So do remember, grams is not standard. You got to move that sucker over 3 places there, guys. So it's 0.005 times a half. And don't forget to do the square. So many people forget to do that last little thing of squaring it. It makes a huge difference. Woo! 100 joules of energy, guys. Isn't that exciting? 100 joules of energy that thing could have. Okay? So what about a car going only a puny 14.1 meter per second? What's 1,000 grams? That's not kilograms. That must be one of those smart cars that's like the size of a clown car. I don't know. So same story, 1/2 the mass. Don't forget to square that thing, and pew. Hey, it looks like it's the same energy of that bullet. It's not. It's kilojoules. It's 1,000 times the energy because it's much, much more massive. More than 1,000 times more massive. It's much, much more massive. So it's going slower, but it's much more massive. Okay? So this car can do a lot more damage than a bullet can. Okay, this is 30 miles per hour, guys. You don't want to be hit by a car going 30. That's going to do a lot of work on your body. Yep, that bullet will do some work on your body too, but not as much. It'd be like 1,000th the work total. Okay, it doesn't mean it doesn't do damage if it does it to a small area. This does it to a large area. Alrighty, so it causes a change, this work. So what we're looking at mainly today is horizontal stuff. So we won't be concerned with the gravitational potential energy because for the rest of this, we're just going sideways, not up or down. So there won't be a change in energy vertically. All right, here we go. Doing some work, moving that box there. It gets pretty exciting here. So how do you get that 1/2 mv squared? Well, guys, when we're doing this work, the force is a FMA, right? We'll make it easy. It's called a constant force. So we have a constant acceleration. And when we have a constant acceleration, that constant force, remember this is equation number 3 on your equation sheet. As you're going down on there, equation number 3, that equals, well, basically that 2ax. But, so solving for the acceleration, and you toss this whole thing right in for the a. So it's the m times that, then you got to do that 1/2 on everything, and then the x cancels out over there, and it gives you one of those things. So when we're not going vertically, we don't have a change in potential energy, but we still do have a definite change in kinetic energy. So any work you do gives something kinetic energy. If it's negative work, that means you're losing kinetic energy. Okay? In other words, this final will be less than the initial if it's negative work. All right, let's do some practice stuff in a moment, I guess. So kinetic energy 1/2 mv squared. Can we state a very important physical principle? Well, I hope so. It's the work energy theorem. The work done by resultant force, that means the net force is the key. Not just any force. I'm pushing on this desk right now. I know you can't see it. It's not moving. I'm not doing any work. There's no net force. There's no change in kinetic energy at my desk. Okay? So it's the net or resultant force over some distance causes a change in kinetic energy, whether you add kinetic energy or subtract. All right, guys, let's shoot some bullets into some clay, some mud bank. Shooting some bullets in the mud. Sounds like fun. And it goes in and stops 6 centimeters later. Remember, that's not standard 6 centimeters. What's the stopping force? And it went in at 80, so that's not a very fast bullet. That's like 170 miles per hour. That's going to leave a mark. But anyway, what's the average stopping force acting on that thing? Well, how we treat that is the work causes the change in kinetic energy, but there's no final kinetic energy here. That's a 0, so that makes it easier. We know the mass of the bullet. We know the velocity. Now we know a distance that the work is done over. Now we're solving for the F in that work formula. Okay, so that's 0 because it ended up at rest. So force times distance. So it's a negative here because it's going to be a negative force because it's a backwards force doing negative work, slowing it down or taking energy away. Alrighty, so there it is, guys. So to solve for the F, remember we change it from centimeters to go 2 places over centimeters. It's only 2 places over. So you divide out by the 0.06. Don't forget to square the 80 though. And so its bullet had 64 joules of kinetic energy. It lost that because of that force pushing backwards. So now to find that force, it's negative 1,067 newtons. Okay, in sig figs, it's like maybe 1,100. Actually, we only have one sig figure there. So in reality, the answer is negative 1,000 newtons. That's a pretty iffy number. Okay, so that's the average force acting on that thing over that 6 centimeters. All right, any questions? You have to ask me later. So the work to stop the bullet equals the change in kinetic energy. That's called the work energy theorem we're using to solve some problems there. Hey, bus slams on the brakes to avoid an accident. Oh, goodness. Leaves some skid marks on the ground, and they're 25 meters long. So if we know the coefficient of kinetic friction, because it's skidding to a stop, brakes are locked up. Look at that. Heating stuff up. What's the speed before applying the brakes? Hey, one more thing I might mention back here on this whole bullet thing is 0% efficiency there because you lost all of your energy to some form. So where's the missing 64 joules, guys? I forgot to bring that up. Heat energy. It warmed the clay up. You're shooting stuff in the clay like that, it warms the clay up, warms the bullet up because of that friction. So we added 64 joules of thermal energy there, which we can't get back. So it's 0% efficient because we lost all of our energy to thermal energy. All right, let's go back to this braking. I brought it up because we're going to lose our energy once again here, stopping. So it's the same story, guys. It's negative work because it's pushing backwards. The thing that's taken away the kinetic energy is friction pushing backwards. So that's what we're setting up. So that work equals the change in kinetic energy. But the work this time is by a friction force, and to find the friction force, kinetic friction force, it's the coefficient times the normal force, and then since we're on a flat level ground, that normal force is just the weight, mg. So times the x, this times the x, that's the work done. Now we got to find the change in kinetic energy there. So that's the work done. It's going to be negative because it's backwards. Alrighty. So you don't really have to put that negative there. Because it actually takes care of itself when you have the negative over here, but whatever. So final kinetic energy in this case is 0. So now we're setting that equal to that. Oops, there we go. So change in kinetic energy equals the work done. Alrighty. So before I get to the last thing, I'm going to do a little bit of scribbling here if I have time. Oh, 37 seconds. My goodness. I'm going to stop right here, guys, because I can't quite finish even though we're almost at the end. I want to show you the relationship between velocity and displacement is kind of an important thing. So we'll do a little part two thing in 3, 2.